Good morning to you all, students. I want this class to be interactive because I wanted you to ask me if you have any doubts in the topic covered so far, so that I can explain in detail. Otherwise, I have to just run through all the slides what I have presented, explaining every topic briefly. But if you ask me any specific topic, I can just explain in detail. Apurva, Gunashekar, Sadev, come on, go ahead and ask some doubts. You know, this is a revision class, right?
Yes, ma'am.
Yeah. Then shall I start from third module beginning once again?
Yes, ma'am.
Okay. Wait a moment while I present the screen. Can you see this? Students, can you see the presentation?
Yes, ma'am.
Yeah. Okay, when we started the module 3, we covered topics on data, data storage and analysis, and comparison with other systems, right? So we understood how data volumes kept growing, and it is adding on to the already existing mountainous data. And also we have seen what are the large number of data sources available in the market. And some organizations generate data, whereas some organizations pool the data. Means they collect the data on behalf of the organizations and pass the data for them to analyze and derive some valuable conclusions from the data. So what are the general data sources available? New York Stock Exchange, FB Post, Ancestry.com, which actually create the genealogy, ancestral trees, that stores around 2.5 petabytes of data, and even Internet Archive, the Large Hadron Collider of Geneva, which is trying to simulate the Big Bang theory that may evolve into this universe. How exactly it happened? They just wanted to study. So for that, they are using this Large Hadron Collider in an underground setup where it is generating around 15 petabytes of data per year. Now, data footprint kept on growing, like carbon footprint, carbon emissions, what every individual do. Even in every individual is now responsible of creating lots and lots of data due to advent of this digital era. So machine logs, RFID readers, sensor networks, vehicle GPS traces, retail transactions, all these are playing very important role in adding to the data footprint. Now, machine logs is in any manufacturing unit. If you automate the system. In that case, how exactly the machines are working, what each parameter is doing in generating the final output, or how different raw materials are being used to produce the final product, and how each of these parameters have to be used in an optimized way in order to increase the production and reduce the resource utilization. All these have to be kept track of in order to optimize the production capacity. And even the RFID readers are deployed everywhere, right? When you go to a mall, you go there to the parking, and that will generate a slip for you in order to keep track of the parking time and accordingly give the bill for you. Their RFID readers work, and even when you're going to the airport, you see the fast tags. There are also RFID readers automatically read the car number and they see what is the associated wallet and try to reduce the total amount from the wallet itself, right? These are all generating lots of data. All these are treated as transactions, and each transaction is kept track in order to analyze and draw some insights. And even sensor networks in order to read the climate or in order to understand the climatic conditions of a particular area or throughout the globe, and capturing the air temperature, humidity, and water wetness of or moisture content of the soil. For everything, sensors are being used, and these generate lots and lots of data. Even vehicle GPS traces in order to optimize the logistics, in order to plan the fleet that has to be maintained. See, because of this COVID situation, now the bus can't run with its full capacity. Only half of the passengers can be accumulated. In that case, how many buses have to be actually deployed in a particular route in order to meet the requirements of the passengers? All these can be kept track. Some planning can be done. Some strategies can be implemented by using this vehicle GPS traces. Even in retail transactions, when you go to a supermarket, you buy something, they are recorded and they'll be analyzed in order to know the customer behavior, purchasing behavior, so that they'll be able to understand what are the things that are frequently bought together, so that they can arrange them at the same place in the racks, so that they can enhance the user shopping experience and bring the users back, retain the users or retain the customers with their particular brand. The data is being made available publicly, and it is increasing year by year. Most of the data is made publicly available on Kaggle platform and UCI Learning Repository, University of California repository, Stanford Large repository, and many other such publicly available data sets are available to data scientists in order to analyze and start playing with this data analysis techniques in order to gain some expertise, so that they can really work on the real-time data sets and come up with good performing models for unforeseen situations. Now, success of any organization in the future will be dictated by their ability to extract value from data of other organizations in the business chain rather than silo-based analysis. Means organizations no longer depend on their organization's data. They have to reap benefits by analyzing the data of other organizations also in their business chain, so that they can optimize the entire supply chain and gain larger market share. And even complex algorithms may not work with large amounts of data. Though data is liberally available, challenge lies in storing and analyzing the data. So data scientists are working on more and more number of complex algorithms in order to analyze large amounts of data and draw some valuable conclusions out of it. Now, the access speeds have not increased at the same pace as the storage capacities of hard drives over the years, right? In initial days, 1 GB pen drive used to be very costly. Now it is coming for a nominal price, right? That is why the storage capacities seems to be increased by reducing its cost, but the access speeds have not increased at the same pace. One typical drive, if you take from 1990, it could store up to 1,370 megabytes of data and had a transfer speed of 4.4 megabytes per second. So you could read all the data from a full drive in around 5 minutes. But over 20 years later, 1 terabyte drives are the norm now. But the transfer speed hasn't increased that much. It is around 100 megabytes per second. So it takes more than 2.5 hours to read all the data off the disk. So writing onto the disk, if you consider, it is even slower than reading the data. So these all adds to the complexity in the task of analyzing large volumes of data. So the obvious way to reduce the time is to read from multiple disks at once. right? So rather than reading from a single disk at a time, if you can partition the data, distribute the data across multiple disks, you can provide multiple access to all those disks to read simultaneously at the same time, so that you can quickly read the data or write onto the disks. Now, the problems encountered during storage and analysis of large volumes of data is hardware failure. When you try to use multiple machines in order to provide shared access to read or write the data, in that case, the chance of a particular system failing will increase. As you increase the number of machines or nodes you use to store the data, automatically the chance of their failure also increases, right? The probability of failure increases. Not exactly the chance, the probability of failure increases. Now, the data loss also is a main problem. Because if the system fails or if a node fails, the data may be corrupted or sometimes permanently lost. In such cases, there are alternatives like RAID, redundant array of independent or inexpensive disks, or HDFS clusters, Hadoop distributed file system clusters, where exactly you can give some replication factor to the data. Means you can store multiple copies of the data. So that though if one data is corrupted or lost, that will be still available. The copy will be still available on a different node in order to read that and finish the processing task. And even fragmentation of data will be useful. When you divide the data onto multiple nodes and store them in the form of blocks, then when you are trying to analyze the data or process the data, you can simply write some map or reduce functions and transfer those functions to the data nodes where the data, a block of data is actually residing, and get the different fragments of results, and finally consolidate all the results to give a generalized or consolidated output. What is the use of this fragmentation in this case? You are able to provide shared access to the HDFS clients, so that the data can be read quickly, processed quickly, and at the same time written back to the HDFS cluster or the RAID disks. Now, Hadoop provides a reliable, shared, storage and analysis system. Shared storage means one file is not stored on a single disk. It is divided into blocks of data and stored on multiple disks, so that you can read that file simultaneously from multiple disks, so that you can reduce the read time. And also it increases the analysis speed of analysis. Now this MapReduce, we tried to compare it with various systems like RDBMS, volunteer computing, and grid computing. Now, when we tried to compare this MapReduce with RDBMS, we understood under the categories, we understood under some criteria like what is the latency in the disk operation, and how is the data access pattern, and how is it actually processed. All these are the criteria we have gone through. Now, why can't we use databases in place of HDFS? Do we need to, when we have larger storage capacity available now by grouping many nodes into a cluster, why can't we satisfy with RDBMS? Why do we need to go for MapReduce? Why is actually this MapReduce technique required? The seek time is playing an important role here. The seek time is improving more slowly than transfer rate. So it characterizes the latency of a disk operation, whereas the transfer rate corresponds to a disk bandwidth. Now the data access pattern is also dominated by the seeks, right? So if a file has to be read by a read-write head in a disk, it has to go to the appropriate disk and appropriate track, and then the appropriate sector, and then find the block of the file located on that sector, and then read that data. That takes a lot of time. It will take longer to read or write large portions of the data set than streaming through it, which operates at the transfer rate. Now, a traditional B tree, if you take in RDBMS, it works well only for updating small proportions of records in a database. But if you're trying to work with large amounts of data, then that will create a bottleneck. Now, MapReduce uses sort or merge technique in order to rebuild the databases. Now, these are the main things we have seen how these actually can be differentiated. These two technologies can actually be differentiated. They are differentiated with respect to data size, access, they provide and updates, they entertain, and the structure, integrity, and the scaling. Traditional RDBMS, we can work only with gigabytes of data, whereas MapReduce supports petabytes of data analysis. And even the access pattern in RDBMS, it is interactive and it is a batch access, whereas in MapReduce, it supports only batch and it doesn't actually support interactive, but it can still keep the client informed about the MapReduce jobs that are running at the background. So this is mainly useful for write once and read many times approach. Means you can write once, the data can be written once, but you can read it multiple times very quickly to analyze the data. But that doesn't happen in RDBMS. It supports read and write many times, but it can be done with slower speed, and only small amounts of data can be updated if at all you want to update the data. And even the structure, traditional RDBMS provides a static schema. Once it is defined, it can be changed. But in MapReduce, you have dynamic schema. It supports column databases like, say, Cassandra, where you need not specify the structure of the data. You start storing them, it will assume that particular structure of the data. And even integrity. Integrity is high with RDBMS because we have several authentication mechanisms deployed at every stage. But in MapReduce, the integrity of the data is less. Why? Because more and more number of nodes are participating in the analysis process, and we do not know which node fails at which particular point of time. So the consistency of the data is still a matter of concern, but still that can be addressed by using HDFS mechanisms like failover fencing, failover technique and fencing technique. And even in with respect to scaling, if you want to increase the capacity of processing, it is not possible with RDBMS. It is non-linear. You can't quickly start deploying the nodes into the cluster. But with MapReduce, the scaling is linear. So you can start adding more and more nodes as per the demand arises to analyze larger and larger volumes of data. Now, in the next class, we have seen how to we compared this MapReduce with volunteer computing and grid computing also. Let's see how we have gone through those topics. Okay, in this module, 3 second lecture, we have covered topics on grid computing, and we compared it with the Hadoop components and even volunteer computing also. Now, in this grid computing, which is also called as high performance computing, have been doing large scale data processing for years. This is being used to process larger volumes of data from many years, but they use application programming interfaces as message passing interface. They don't have a specific technology which actually forms the interface between the client and the nodes that are actually storing the data. The approach in HPC is to distribute the work across a cluster of machines which access a shared file system hosted by a storage area network. So on this storage area network, lots and lots of machines, clusters of machines are maintained, and they provide shared file access. Means any file has to be read, that can be still read from multiple machines, as we do in MapReduce. This works well predominantly with compute intensive jobs, but it becomes a problem when nodes need to access large data volumes, since the network bandwidth is the bottleneck and compute nodes become idle in some situations. We can say that grid computing is having almost the same architecture as MapReduce. But what is the drawback that we confront with this grid computing, and how this has been overcome by using MapReduce? In grid computing, you can't read larger and larger volumes of data without facing network bottlenecks, right? Because the data has to be transferred between different machines in the cluster in order to consolidate them at a place and perform the processing, right? So the data has been the data will be transferred in this architecture from one machine to another machine in the cluster. This will utilize lots of bandwidth, and it creates bottlenecks in the bandwidth utilization. Now, MapReduce, how does this overcome? How is this problem overcome by MapReduce? MapReduce tries to collocate the data. Understand this term, co-locate. Co-locates the data with the compute node, so data access is fast because it is local. This concept is called as data locality. Data locality is supported by MapReduce by collocating the data with the compute node. So wherever the data has to be processed, the function will be transferred to that particular node, and the data will be processed and get the result back and consolidate all the results from such independent processings that have been done on splits of data, input splits of data. MapReduce operates only at the higher level. The programmer thinks in terms of functions of key and value pairs, and the data flow is implicit here. Data flow is not actually shown how it is running between the map and reduce jobs, but everything is handled at an abstract level in the form of key value pairs. And coordinating the process in a large-scale distributed computation will be a challenge in case of grid computing, because there are multiple machines running at the same time, and clients read the data from multiple machines in grid computing. But there is no one such component which actually takes the responsibility or accountable in order to coordinate all these tasks. But MapReduce provides for such responsible components in order to take care of the entire jobs being run on multiple nodes. Failures also should be handled gracefully. If a node fails, or if a machine fails on the cluster, they should be handled gracefully. The client should not have an experience of the task being interrupted due to system or data failures. So this MapReduce implements failure detection mechanisms through shared nothing architecture. This is not available in grid computing. When some node fails, it actually imposes some interruption in the analysis process in grid computing. But that is not the case with MapReduce. It implements some failure detection mechanisms which are also which are implemented through shared nothing architecture. But message passing interface programs have to explicitly manage their own checkpointing and recovery, which gives more control to the programmer but makes them more difficult to write. This happens with grid computing. These message passing interfaces programs have to explicitly manage their own checkpointing. Yeah, they are overburdened with maintaining their own checkpointing and recovery. If some task fails in the middle, read or write task fails, then they have to run back to their previous checkpoint and retrieve the data. So the data in this intermediate stage will be lost, but that doesn't happen with MapReduce. It automates the checkpointing and recovery mechanisms. Now, MapReduce might sound like a restrictive programming model because large range of algorithms can be, because we try to write everything into a particular task, say a map task and a reduce task. Now, if you want to analyze some different kinds of data types, then we may face some problem while writing the mapper and reducer classes because it makes it more and more complex with changing types of data when we are writing the mapper class and the reducer class. A large range of algorithms can be expressed in MapReduce, from image analysis to graph-based problems to machine learning algorithms, and though it is covering diverse range of problems in order to solve those particular problems, still it is somewhat restrictive programming model. Why? Because it makes the framing of this mapper or reducer classes, writing of this mapper or reducer classes little more complex. Why? Because it is supporting wide range of domains in order to analyze the data. Now we have also compared volunteer computing with MapReduce. In this volunteer computing, we quoted the example of SETI at home, that is search for extraterrestrial intelligence. For this, large volumes of radio telescope data have to be analyzed in order to arrive at some conclusions like whether there is any, say, extraterrestrial life outside in the universe other than on Earth. For this, volunteers donate CPU time from their otherwise idle computers to analyze radio telescope data for signs of intelligent life outside the Earth. Even you can donate. You can just register to this SETI at Home project so that when your computer is idle, when your CPU time is available, they send you chunks of data, work units of data, so that you can keep running them, and they will take around 2 to 3 days to run each work unit, and the results of that analysis can be sent back to them so that you receive newer work units to analyze them when your computer is free. Right? This is how each person is volunteering to the project so that they need not set up at same place too much processing capacity. They can rely on volunteers throughout the globe in order to analyze this radio telescope data. Other such programs or projects are Great Internet Mersenne Prime Search, where they are searching for the largest prime numbers possible, and even Folding at Home, where they are trying to study the folding of proteins, which actually results in introducing some diseases into the body. Which results in introducing in some diseases into the body. Now, this volunteer computing projects work by breaking the problem, as I said, into work units. They are trying to solve into by making them as chunks of data, work units of data. They may be of approximately size 0.35 MB, which will be transferred to the volunteer's computer and analyzed there and get the result back. And when the analysis is completed, the results are sent back to the server and the client gets another work unit. But as a precaution to combat cheating, say a volunteer can say that he has analyzed that data but actually didn't do that. So to combat such kind of cheating, each work unit is sent to 3 different machines across the globe again and needs at least 2 results to agree to be accepted by the server. Right, this is say cheating combating mechanism. Now, both volunteer computing and MapReduce use fragmentation technique. Means both divide the data into work units. Even in MapReduce, the data is divided into blocks of data and distributed across the nodes on a cluster. And even in volunteer computing, they divide the data set into smaller chunks of work unit and distribute to the volunteers to perform processing. But what are the differences? Where they exactly differ? SETI at home problem is very CPU intensive, which makes it suitable for running on hundreds of thousands of computers across the world, because the time to transfer the work unit is dwarfed by the time to run the computation on it. Notice this. In MapReduce, where we run this task in a single data center, we are trying to minimize the data that is being transferred between the nodes by transferring the map and reduce functions directly to that node, so that data need not be transferred, but function, because it is very small, it can be transferred to the node where the data is residing and run that map function or reduce function on that particular data node. But in volunteer computing, you transfer the data or work units to the volunteer's computer. And this transferring the work unit, the time taken to transfer the work units is actually very small when compared to the time taken to run that voluminous data if it is run at a single place. That is the difference between volunteer computing and MapReduce. Volunteer computing takes help of machines situated across the globe, whereas MapReduce runs on machines on a cluster in a single data center. And volunteers donate CPU cycles, not the bandwidth, remember. But MapReduce tries to save on the bandwidth. And MapReduce is designed to run jobs that last minutes or hours on trusted, dedicated hardware running in a single data center with very high aggregate bandwidth interconnects, right? All the machines are trusted because they are owned by an organization's data center. So you can run the processing task on dedicated hardware which are trusted. But in SETI at home, in projects like SETI at home, which use volunteer computing, it runs a perpetual computation on untrusted machines. A volunteer registers to the project and the work units are sent to them. They are untrusted. Those volunteers are not checked actually. They are sending the work units to be run on untrusted machines on the internet with highly variable connection speeds and no data locality. Data is being transferred to a further off location. The data locality concept is not being followed by volunteer computing. So what are the main differences here is volunteer computing runs on untrusted machines, whereas MapReduce tasks run on trusted and dedicated machines. And data locality is implemented by MapReduce, whereas volunteer computing doesn't use the concept of data locality. And volunteer computing wants to transfer the data to and fro, whereas MapReduce tries to minimize the data transfer between the nodes. These are all major differences between volunteer computing and MapReduce methodology. And brief history of Hadoop we have gone through. They're quite direct. I think it doesn't need any deep explanation. In which year they actually started on this idea and how it finally evolved into this Hadoop platform. All these are explained chronologically by taking year by year progress, how they have achieved higher processing capacity. Okay, we'll also cover this third lecture so that we'll finish third module revision today, and tomorrow we can start with the fourth module. Topics I have recapped so far. If you have any doubts, you can come up with that. All these are straight topics, right? There is no complexity in understanding them. They just discussed about various types of technology, how they are suitable to some scenarios, and what drawbacks they are having, which doesn't suit that particular context, which led to the introduction of this HDFS and MapReduce technologies by Hadoop. That we have seen so far. That is why it is quite clear and straight to understand. In this lecture, we again covered Apache, Hadoop and Hadoop ecosystem and Hadoop releases. Now, under Hadoop ecosystem, we have seen various types of projects that are available. HDFS and MapReduce are the critical components of Hadoop, but still there are many other projects which also fall under this wide umbrella of Hadoop platform. And although Hadoop is best known for MapReduce and its distributed file system, the term is also used for a family of other related projects that fall under the umbrella of infrastructure for distributed computing and large-scale data processing. So when I say HDFS, you should immediately remember a term, key term, distributed computing. And when I say MapReduce, you should immediately it should strike your mind that it is used for large-scale data processing. HDFS is used for distributed computing and MapReduce is used for large-scale data processing. Now, all of the core projects are hosted by the Apache Software Foundation, which provides support for a community of open source software projects, including the original HTTP server also. So not only on a single machine, you can transfer this processing capacity across various machines by using HTTP protocol. And even you can work on data situated at different data centers also, not only on cluster in a single data center. Now, other Hadoop projects we discussed are common, which includes a set of components and interfaces for distributed file systems and general input-output. And this implements serialization, that is converting your Java objects into byte streams and again back into Java objects, which is mainly used for transferring large amounts of data across the network. And even Java remote processor calls are implemented by common, and persistent data structures are used in order to store the data by using this common project. Pay attention to these projects. Lots of questions may come from this. Why? Because each technology has its own set of features and they are meeting some good set of requirements from the clients. So you just see what each project is serving, what types of features it is having. And Avro is another project which is a serialization system for efficient cross-language remote processor call and persistent data storage. So if you want to interact between the nodes which are having data with different, which run on which use different languages. In that case, we can use cross-language remote processor calls in order to communicate between them, and they also have persistent data structures for the data storage. And MapReduce, we have already seen, it's a distributed data processing model and execution environment that runs on large clusters of commodity machines. I say commodity machines because now machines cost has come down, and when the demand arises, immediately you can increase the capacity of your cluster, scale up the capacity of your cluster by just adding them as nodes, just by plugging in the nodes and harness their capacity to the already existing cluster. And HDFS is a distributed file system that runs on large clusters of, again, commodity machines. This makes the scalability of the architecture easier at a lower cost. So if you want to work with larger and complex sets of data, that is not at all a matter of concern. Why? Because you can immediately scale up your cluster architecture also by adding multiple nodes. And PIG is another project. It is a data flow language and execution environment for exploring very large data sets. And PIG runs on HDFS and MapReduce clusters. So you have a query language, it is like a scripting language to process the data which is stored on HDFS. So if you want to write some scripts, write some programs in order to analyze your data at the backend, that can be done through this PIC. It is a data flow language and execution environment for working with large volumes of data. And Hive is like your SQL. It is a distributed data warehouse, and Hive manages data stored in HDFS and provides a query language based on SQL, and which is translated by the runtime engine to MapReduce jobs. Means on the front end, you write your queries to question your data set, and these queries called as Hive, this is also called as Hive query language, HQL. These Hive queries are translated into MapReduce jobs at the backend and by the runtime engine, and then these jobs are run on various data nodes in order to actually extract the answers or responses for the queries you have posed to the data set. So it is mainly used for querying the data on the clusters of HDFS, and even HBase is another project under this Hadoop platform. This is a distributed column-oriented database, and HBase uses HDFS for its underlying storage. Means HBase lies on the top, under which the HDFS architecture is actually maintained, and this HBase uses this HDFS architecture to store the data and supports both batch style computations using MapReduce and also point queries which uses random reads. HBase supports both MapReduce as well as point queries, which actually runs on RDBMS. That is on relational databases. Another project is Zookeeper, which is a distributed, highly available coordination service. And this Zookeeper provides primitives such as distributed logs that can be used for building distributed applications. So this Zookeeper is like a monitoring service. When multiple access is given to nodes on to the data stored on HDFS clusters, all these should be properly coordinated. Otherwise, some bottlenecks may arise while transferring the request from clients to the HDFS cluster. So this Zookeeper acts as a coordination service which actually coordinates this entire flow of tasks. This Zookeeper provides primitives such as distributed logs that can be used for building distributed applications without having any problems in reading or writing the data, performing read or write tasks. And Scoop is another project. It is a tool for efficient bulk transfer of data between structured data stores and HDFS. Because data can be first read as RDBMS into RDBMS, and then it can be transferred in bulk to HDFS clusters. In order to perform such efficient bulk transfer of data between RDBMS and HDFS or any structured data stores and HDFS, Scoop can be used. And OC is a service for running and scheduling workflows of Hadoop jobs. Workflows means you have the predefined components. You have a component for extracting the data, you have a component for transforming the data, you have another component designated for loading the data and then pre-processing the data, analyzing the data, and finally visualizing or testing the analysis results. All these components can be deployed by creating the workflows. Now, OC is such service for running and scheduling these workflows of Hadoop jobs, including MapReduce, Pig, Hive, and Scoop jobs. All can be scheduled as workflows by using this OC interface. And we have also seen Hadoop releases, what are the features provided by Hadoop 1.x and what drawbacks they have, and how various other features like HDFS Federation and HDFS High Availability are introduced in Hadoop 2.x release. And also another important feature called as Yarn, that is yet another resource negotiator, which is a general resource management system for running distributed applications. How they provided they added features to this 2.x version we have gone through in the previous lectures. So the main three features added in this Hadoop 2.x version are Yarn, HDFS Federation, which partitions the HDFS namespace across multiple name nodes to support clusters with very large number of files. In Hadoop 1.x version, you doesn't have this mechanism of HDFS federation. So only one name node will be responsible to store the entire metadata of blocks of data stored on data nodes. But if the data volumes increases, this name node can't store that larger volumes of metadata. So in 2.x release, HDFS federation have been introduced where it partitions the HDFS namespace across multiple name nodes so that one name node stores the data under a particular root and the other node stores the other name node stores the data under another particular root rising out of another particular root so that the metadata can be stored being partitioned onto various name nodes. So though the data nodes keep increasing, still the name node has the capacity to just accumulate all that metadata of those data stored on the data nodes. Now HDFS high availability removes the name node as a single point of failure by supporting standby name nodes for failover. So if a name node fails, what will happen? Normally for one particular root of file system, one name node will be maintained. Say if that name node fails, you should not lose the entire metadata about the data nodes, right? Because name node will help us to reconstruct all the blocks of data distributed across the data nodes. That is why if the name node fails, the data will be lost. But HDFS high availability ensures that there is a secondary name node that takes up the responsibility of primary name node in case of any primary name node failure. And what are the features provided by Hadoop? Different releases are given in a consolidated table here so that you can have a bird's eye view of what all are the features supported by various versions. Okay, this is how we finish the revision of module 3. Students, do you have any doubts in the topics discussed so far? Okay, shall we end the meeting and meet tomorrow for the next modules revision? Harini?
Ma'am?
Any doubt?
No, ma'am.
Okay, shall we end the meeting then?
Yes, ma'am.
Okay, see you in tomorrow's class. Bye.
Bye, ma'am.